The mechArm 270 Pi is a 6-axis collaborative robotic arm developed by Elephant Robotics, and it's one of our favorite to work with here at Neuracore. What makes the mechArm 270 Pi particularly special is that it was designed with education and development in mind. It's the kind of robot that lets you focus on the interesting problem, like making it perceive and interact with its environment, rather than getting bogged down in complex hardware setups. Universities, research labs, and developers use it to prototype real manipulation tasks, which is what we're going to be doing today. It's lightweight, reliable, and with Neuracore behind it, you can go from zero to trained deployment-ready model faster than you might think. Now the mechArm 270 Pi comes with a variety of attachments so you can tailor it to whatever your needs are. For these demonstrations, we will be using the micro suction pump and the G-shape base 2 attached. Alright, let's get into it. But first things first, let's record the dataset. Okay, so I've got the script now running, and as you can see here on the screen, we have got everything streaming from the mechArm 270 Pi and from our method of teleoperation today, which is the MetaQuest Teleop. Both of them you can find available open source on our GitHub. As you can see here, we are using the Oak camera. We have two frames, left and right, because this is a stereo camera. We have all the inputs from the joints and our URDF visualizer. We have configured already our MetaQuest with the hand controller with a few buttons on it that for the operation you have to press A to enable it to start moving, and we have B, which sends it to a predefined home position. And for start and stop recording, the joystick's button will control that and will toggle the state of recording. For the gripper, which in this case is a suction cup, we mapped the analog trigger button to the suction action. At 50%, it triggers it to start the suction action, and below that, it stops it, basically equivalent to what you would have with a parallel gripper. In order for us to make sure that teleoperation is deliberate, we added a grip button that acts as a dead man switch on the hand controller. That is, you're not going to be able to move the robot when it's active unless you're holding this button and moving the robot actively. So if for any reason you end up leaving the controller, the robot isn't going to move and follow you. Also, please make sure that your head stays as straight as possible, because the tracking happens between the hand and the headset. So any motion in the headset will be translated to an error in the hand controller. This is helpful in case you have to move your body, so the whole tracking will be relative to you and that wouldn't cause any issues. But also it comes with a caveat that if it moves on your head or on your chest, as I'm mounting it right now, this will introduce some errors. So now we move on to training. As you can see, we can navigate there from the side panel. I have already navigated there, so we can go and create a new training job. When we create a new training job, you will be giving it a name. For the sake of this demonstration, I will be calling it Elephant Robotics Demo. And then we will select the frequency at which the policy will be running at inference time, and also the frequency we'll use to synchronize the dataset and training. It's good to always know what your hardware is capable of, and for the sake of this demonstration and the setup we have right now, I know it's about 10 Hertz, so I'll be selecting that. Also good to know that one feature that we have at Neuracore is that we record everything aperiodically. That means that whenever you want to change the frequency, we can resynchronize at the frequency you choose, which is definitely better than recording at a set frequency. And if you figure out later on that you need a higher or a lower frequency, you will need to redo the whole data collection again, which is usually the most expensive part. As for the dataset, you can go on and select any dataset that you have collected. I will select my dataset here. It will start showing up the data types that I have and what I can be training on. So for the algorithms, I will go and choose one of the algorithms that we provide here at Neuracore. For this task, I'll choose the diffusion policy, which is powerful enough for the task we want to perform. I will choose that this algorithm will look at RGB images, joint position, and the gripper values, which in our case is a suction cup. And I want my algorithm to output the target positions for my joints and the target value for the gripper. We have also in the compute resources, we have smart allocation enabled by default. And what it does is basically it looks at the size of your model and the size of your data set, and it suggests the configuration of GPUs that you train on. If you don't want to do that, you can go on and change it. Just for the sake of this demonstration, I'll change this to V100. You can also go and change the advanced options if you want. Here you will see that we have the training parameters and the algorithm parameters. The auto batch size will try to fit the biggest batch size in the VRAM of the GPU that you have selected. If you have a set number, you can select it. For instance, you can pass 64, and you of course can always reset it to auto if you want. The epochs is the number of epochs you want to run the model to train, and the prediction horizon is how many steps you want the action horizon that your model will predict to be. You can of course change the algorithm parameters, and each algorithm comes with its own set of parameters. If you really want to change these, feel free to do that. Otherwise, most of the time, these default parameters will be sufficient. Once you are happy with the job, you can go and create the job, and our platform will take care of creating the virtual machine, synchronizing the dataset, launching the training job, and when you go inside, you will find all the metadata related to the job. And once we have everything spinning, you start to look at the logs and the metrics of your training. So once your training is done, you have two options to roll out your policy. First, you can run it locally, where you can go to the training, and inside the training, your model, once it's ready to download, you can click download and it will be downloaded on your device. We provide a few examples that you can run in the open source repository for the Elephant Robotics example, where you can run the downloaded policy on your hardware. Or the second option, if your hardware doesn't have a powerful enough GPU, or you're using a bigger policy, you can host it on our end. We provide Endpoints, which will spin a virtual machine to host your model. And what will happen is, inside our scripts that we also provide in the example, you can run a remote policy where the script will collect all the observations and states, send it to our endpoint. The endpoint will run the model, compute the action horizon, and send it back to the robot, and it will be running on your hardware. In order to do that, you will go to the endpoints. You can navigate from the side panel and come to deploy. You can select the model that you have already trained. You can give it a name. In this case, I've given it the name Elephant Robotics Demo Endpoint. And you have to select a GPU that you want to run on. I'll just select the V100 for this demonstration. We also provide you with a time limit in case you don't want to leave it running indefinite. By default, it's indefinite. We suggest that you run it for as long as you want, because the cost can accumulate pretty quickly. I'll choose, for the sake of this demo, 1 hour, and I'll hit deploy. Once the endpoint is deployed, the status will turn into activated. You can copy the endpoint name and provide it to the script, which will run the remote endpoint and provide the action horizon to your robot to execute on the hardware. What you're seeing here is a model that has already been trained and an endpoint that is already live. This is a full workflow end to end. So now we have finished recording dataset. It's about 50 demonstrations, which is enough for this robot to work well. We've used Neuracore's Python interface, which is open source on GitHub, and Neuracore's robot visualizer, which you can get for free. So by now, if you've followed all the steps, you should have a fully functioning mechArm 270 Pi that is capable of performing a pick and place task. Whether you're a student, a researcher, or a developer experimenting with robot learning for the first time, this setup is designed to be as approachable as possible. And hopefully today's video shows you how quickly you can get results. If you have any questions, feel free to drop a comment below. Otherwise, thank you for watching, and I'll see you next time.